Okay. Yeah. All right. So we continue our tutorial on G-invariant and G-equivariant neural networks. So we have seen the case of discrete finite groups with discrete generators, and now we are going to look at a specific type of infinite group that has an infinite number of actually uncountable number of transformations, but this one has what we call infinitesimal generators. So it's a special type of continuous group. So Lie groups is a continuous group that use infinitesimal generators. The Lie theory provides a way of analyzing these continuous groups in terms of these infinitesimal generators. And the Lie algebra G of lowercase g of a Lie group capital G is a continuous. You can think of the capital group G as a transformation that lies in a continuous manifold. Okay. So the Lie algebra is essentially describing the tangent space. So if you have a transformation, it's telling you what the derivatives of the tangent space is in the manifold, so that you can use those infinitesimal generators to generate transformations in this manifold, right? So you start at any point, you can just find a way around to find another transformation. So for instance, for rotation, you can think of the Lie algebra as telling you what rotation means infinitesimally. So that now you can from a specific rotation operation, you can push it toward some other larger rotation, right? You go slowly in infinitesimal rotation. So the tangent space is defined like this. Is kind of this is kind of the derivative, the t, and the g is the current transformation. So the Lie algebra is essentially the combination of these two things, which is a vector space of infinitesimal generators for these transformations. And an important aspect of this is the exponential map, which is defined this way, that takes a Lie algebra and then produces the entire group, the continuous group. So it maps back from the Lie group, and you can understand the matrix exponential. You can think of a matrix exponential where you are essentially applying these infinitesimal generators multiple times to get to some, from where you are to some other transformation. Does that make sense? So a classic example is the rotation group, where we are going to have this rotation matrices. They are orthogonal. So this is a special orthogonal group with dimension n. Is these transformations are essentially orthogonal rotations of the space. So that's how you get the car to spin on the example that I was showing like earlier. Okay, so for instance, in a point cloud, if you go apply the special orthogonal group, it will rotate your points around the origin. Okay, so the point cloud will be a collection of points represented by this subset, and you can think of this as earlier we saw as a matrix, right? Also, it could be a set or a matrix. Now, so we have these n data points. There are 3 coordinates. In order, the order that we draw the points is of course irrelevant. Then the first thing that is obvious in a point cloud is that there is a permutation invariance, right, for our representations, or equivariance if we want. But also more than this, there is yet another group, which is a car is a car no matter how it's rotated. So the rotation of the points themselves also shouldn't matter. Or minimally, you want to be equivariant, right? What does that mean? If I don't care where the car is positioned, I should be invariant. If I care where the car is positioned, I should be equivariant, because then my representation will also tell me the direction that the car is going, right? So if you think about Waymo, when they have their cars using the LiDAR, they want to know where the cars are pointed, so they have to use equivariant representation of the point cloud generated by LiDAR. So, okay, so the other thing is that, so for instance, you want to be rotation invariant, and let's say that you also don't care if the car is here, somewhere else, it's still the same car. So there is also a translation invariance that you would like to have. Okay, so there are these three kind of transformations that you want to be invariant to, or equivariant. Okay, so in 3D transformations of an object is a mapping from the space, from this point cloud space to another point cloud space, maps the coordinate points. So we are looking at isometric transformations, or it's also known as rigid body transformations, meaning we transform the car, we don't make it larger, we don't make it smaller. We are looking right now at transformations that don't change the car itself, so that the length is preserved. So whenever you have some norm over the two inputs of this space, or 2-point clouds, whatever the norm is, it's preserved under the transformation, right? Also, the cross products are preserved for these rigid transformations, meaning that if your car is pointing somewhere, then that is essentially like the orthogonality that they have is preserved. So this implies that it preserves the Euclidean distances between every pair of points. So the car integrity is preserved in our example. The angles between the vectors are preserved, so inner products are preserved. Orthogonal vectors are transformed into orthogonal vectors, and that's the property for the cross product. And the orientation is preserved, right? So if you have some notion of right-handed part of the car, what's in the right on the car, from someone sitting on the car, the points that are on the right keep being the right, no matter how you transform them. Okay, so these are rigid body transformations. Now, of course, you can have different properties, and that would give a different group, and then you can be invariant or equivariant to that group. So maybe you don't care about the size of the car. Okay, so let's look at the special orthogonal group SO3 for this 3D rotation group. These are all the rotations of the origin in three-dimensional Euclidean space under the operation of composition. So the group is essentially all the 3x3 orthogonal matrices, and these are denoted as O3. So all possible orthogonal matrices, they essentially rotate your points, and you apply to each of the points. So the thing about the orthogonality of the matrix is that they preserve the length of the vectors, so they are they have to preserve the length of the vectors, right? So they are orthonormal, meaning that they have also a unit norm. The special orthogonal group is an orthogonal group such that the determinant of the transformation is the square is 1, so that it's not, you're not stretching your car. So SO3 has continuous rotations that you can think as between 0 and 360 degrees. And SO3 is also a Lie group. It's a smooth differentiable manifold. Every rotation can be represented uniquely by an orthogonal matrix of unit determinant. For instance, the counterclockwise notation about the positive axis from biangle theta would be something like this. If you want to rotate the x-axis, you multiply by this. You rotate the y-axis, you multiply by this. You rotate by x-axis, you multiply by this. And if you want to rotate by some combination, there's an angle for x, angle for y, angle for z. You just combine them, okay? And then that will give you some all the possible rotations in your group. Okay, other rotation matrices can be obtained by this, of course, right? Using matrix multiplication. And of course, for each of them, the theta is theta for x, theta for y, theta for z. Okay, so what's the exponential map of this group? The exponential map is essentially this, defined as this, right? It's a composition of transformations through the matrix exponential. So if you look at the definition of sine and cosine, is defined through an exponential, right? Of this coefficients here. So essentially, so this is the generator for x, the generator for y, generator for z. So if you pass this through this matrix exponential, you essentially multiplying by some scalar, will give you any of these matrices. Okay, so if you can convince yourself that this could generate, for instance, this matrix by just saying theta times LZ. So theta times LZ, you pass through the exponential, you end up with a matrix like this with sine and cosine. Is that okay? So it's just the definition of infinite series of sine and cosine. If you plug it in and you do this matrix powers, you see that this element here is the infinite series of the sine and the cosine. Okay, so this essentially describes how you can generate your transformations. Now, also note that matrix exponentials behave very similar to the way that exponentials behave. So a plus b is going to be essentially the composition of these two transformations. So for instance, for a rotation that is theta x, theta y, theta z in the three-dimensional space, you're going to multiply theta x by lx, theta y by ly, theta z by lz, and exponentiate, and then you end up with this kind of rotation. So this will end up with a matrix like this, and the exponential will give you the sine and cosine for this rotation, okay, in three-dimensional space. So a rigid transformation can be described then. This special Euclidean group has an extra condition in that you also need to be invariant to translation, right? So right now we are always rotating around the origin, but you also want to be able to say that's invariant to rotate to translation. And when you think about invariant to translations, what does that mean? It doesn't mean just that the car can be translated, but also that you can first translate and then rotate. You see, like the car can end up in some other place, but those transformations can be described as rotations first and then translations. So for those, the Lie algebra will be this will describe your transformations. Essentially, there is an extra coordinate that will tell you what is the position, kind of what's the position of the car. And the way that we do this is we add an extra dimension with the translation, and then the inputs are described with this extra dimension equals 1. And when you apply this, you'll see that once you multiply this operator by x, you end up with the rotation plus the translation. That's defined by this. So that's kind of a trick to get translations there. And you can see that this point here is the same space as this, right? Has the one here. So rigid transformation of direction vectors. So another interesting thing is that if you want that translation to be ignored, you can just start with a point that has a 0 here, and now the translation is not taken into account.
This is kind of homogeneous coordinate.
Sorry?
This is not homogeneous coordinate.
Homogeneous coordinates. Not sure.
No, it was a familiarity.
Oh, okay. Yeah, I'm not familiar with the term. Okay, so what are the exponential maps of the Lie group, right? For this rotation, there'll be 5 groups or 6 generator matrices, which are this. And the trick is, there will be one matrix for each translation on each coordinate, plus the three rotation matrices that we saw before. So the Lie algebra is just a combination of these 6 things. And then you can describe any transformation through the exponential map of these generators, right? So this will be the translation in X, Y, and Z, and these are the angles. Okay? Similarity transformations will also scale your object. So this term here is a scaling term. So if you remember, it was 1 before because you don't change the sizes, but for similarity transformations, you may change sizes. And that's what's interesting is that if you look at how this group behaves, for this group, the outputs of these 2 things are equivalent. So S times the object and the translation is the same as doing this. So essentially, it's a way to scale the points. And then you have an equivalent set of Lie algebra for these generators. So let G be a group in 3D point clouds. Let's say one of these 3 groups. We have seen that any group element can be written in terms of this exponential, right? So any transformation can be written as this generators times some parameter. And then what so you can think of these generators here are the basis vector space of the Lie algebra. So this thing is the Lie algebra, is describing the transformation that you want, and the exponential mapping actually gives you the representation that you're going to actually apply to the points. So a group element is most relevant in how it acts on the transformation of the input. Again, we have this representation, right? I give you a group element, and then it gives me the general linear group, or like a matrix transformation. Then again, this representation satisfies these conditions that we saw before for the representation. So essentially, it describes how the element of the group acts on the object, right? And you can see that the Lie algebra does exactly this. From the Lie algebra, the generators, I can describe how to get from them to the actual transformation that I'm going to apply to my object. So mirroring this notion of group representation, the Lie algebra is effectively describing infinitesimal generators for this for your group, right? For your Lie group. You can think of something like this. So if you were to apply the representation over this exponential map, you can describe it as a derivative of your representation of the Lie algebra through the exponential map. So essentially, the Lie algebra is just telling you what the tangent vectors look like. Okay. So now, if we want to build G-equivariant layers, then it's the same. So now that we have this understanding, like we can use we don't need to operate. You see, the exponential mapping means that we do not need to operate on the continuous manifold. We can operate on the Lie algebra and do all our tricks on Lie algebra, and then apply that through the representation, obtain the right transformation. Okay, so the same thing, for instance, works the same way for G-equivariant networks, and similarly, right, yeah, so the G-equivariant networks have the same exact representation using the Lie algebra to get the mapping. And you note that it's the same basic idea, right? You have this notion of eigenvectors, and now the eigenvectors are created through the Lie algebra rather than the original case that we're looking at the representation. So let's see an example. So here we have the transformations, and then we have the representation of this transformation is going to have this invariance. So we are looking for the invariant subspace that will that for which we can use our neural parameters, right, to live in, which is the same idea as before. Okay. So what we are essentially interested now is on the Reynolds operator for this thing, right? So the interesting thing is that here, instead of trying to just average things, I could go for looking at the derivatives of this function, okay? So if I take a derivative of this function with respect to alpha, this is gonna be 0, and then this derivative of this has to be equal to 0, right? Which is essentially this. So this condition here, the derivative of the exponential for this parameter, right, would just be this this infinitesimal generator times v, okay, which is essentially this. Now, for every single Lie algebra element, you have this condition that needs to be satisfied. So you just need to find a subspace that will satisfy these conditions. Okay. So let me show you what the solutions look like. So what we have is that we have that these infinitesimal generators, right? These matrices that we saw for the Lie algebra, multiplied by v needs to be 0, right? And what we are going to do is we are going to use this matrix here and do a decomposition of this matrix. Okay, we're going to break down into the null space spanned by the columns of Q and the orthogonal complement P. So this will give you the invariant subspace of this matrix, right? Again, we are trying to just look for the invariant subspace. So all symmetric solutions for V must lie in this null space of C, which is, if you look here, right? The null space is essentially just Q beta for any coefficient of beta. Now, you see, we are back to defining the invariant subspace that we need, right? So that this means that if we consider weights W, such that the vectorized version of the weights will be this null space, right? Kind of before we had the basis for our Reynolds operator. Remember, it's the same idea here. This forms a basis that will make sure that these derivatives with respect to the parameter are 0. What does that mean for the derivative with respect to the parameter to be 0? It means that if I do an infinitesimal change, I'm still in the subspace that that is invariant to transformations, right? So I'm always, so once my invariant subspace is defined by this manifold. Does that make sense? Right. So it's the same concept that we had before. It's just that for the Reynolds operator, we don't have to look at every transformation. And while here, we have to look at all of them. So essentially, for the null space of the infinitesimal generators, then this beta is what our alphas are the parameters for our neural network. And then all we have to do then is to learn these coefficients. And then once we do that, we essentially have a way to build our G-equivariant neural network, right? We unvectorize this, and that will give you a equivariant mapping. So there are like many. So that's a practical method, right, to obtain these equivariant layers. The question is whether we can have some arbitrary functions from a vector space V1 to R and V1 to V2 that can be made invariant or equivariant. And the thing is that it's really true, since we have one thing that we can always do, right? We can always do this, the Reynolds operator procedure. So one thing that if your transformations are nonlinear, right? If you have nonlinear transformations, but you have a finite group, you can essentially just average over your. So if you have a neural network here, you can just average your embeddings over each transformation, and that will be invariant. So you're essentially applying the Reynolds operator through the embeddings of your neural network. And similar to the Reynolds operator, though that procedure is going to be invariant to permutation, right? And similarly, you can also define a equivariant procedure by just averaging from the group. The challenge for this procedure, so this allows you to build equivariant and invariant neural networks from arbitrary transformations. And actually, your neural networks here, they do not need to be specifically designed to be invariant or equivariant. They can be essentially anything. But the problem with this is when they have a large cardinality of the group, then this notion of exact averaging is intractable. And in those cases, you can approximate the sums through heuristics like Monte Carlo. But there is a somewhat recent method that has an interesting idea, which is as follows. So if for a given input, I may not need to look at average over all transformations. What does that mean? It means that, so suppose, for instance, that I'm doing a permutation invariant function, right? And my input, all the values are the same. If all the values are the same, I do not need to consider all possible permutations. Okay, right? I just don't need to. I just look at the identity function, and that's good enough. Now, suppose that I have a large vector, and all elements are the same except for one. I do not need to look at all permutations. I just need to look at this element moving around this vector, and that's it. Right? So I don't need to average over the entire group. So the idea of this work is that instead of considering all possible groups, all possible transformations of the group, you really, for a given input, an input, you just need to consider the transformations that are necessary for that input, right? And that's what they call a frame, which are all the transformations that are needed for that specific input. And the concept here is to build then an equivariant frame. So I'll give you even it's an interesting case because even for the Reynolds operator, you can think of building Reynolds operator specific for some specific inputs. So for this input, the Reynolds operator is this. For this other type of input, there is a different Reynolds operator because the group is different. That would increase your expressivity because if you are removing elements from the group, now your rank is going to be larger, right? You're going to have more eigenvectors. You're going to have more power, more parameters for your neural network, right? So that's increases your expressivity, and it's a really cool idea, right? Because so what happened is that we wrote this paper 2019 where we said, oh, we can use the Reynolds operator and do this thing, but then we were talking about sets, and for sets it's kind of silly to think of constraining all the elements are the same, like it's not something that ever crossed my mind. And when this paper came, I thought it was really cool because if you define your transformations based on the inputs, now you don't have, remember when we were doing the permutation, right? And we just had two eigenvectors. But if you consider just a subset, then you could have a lot more. You can have a lot more expressivity, a lot more parameters if you condition your transformation on the input. And that's essentially this notion of frame averaging. So for each input X, you're just going to find the Reynolds operator for that input that's necessary for that input. And everything that we saw so far is applicable in that case. And more specifically, if you have nonlinear transformations from which you can learn these eigenvectors, you can essentially apply your neural network just to the transformations of this group, which are probably much smaller than the original one. And you can build invariant functions and equivariant functions this way. That's a great question. And it really depends on the task or the type of input. So for instance, they looked at point clouds, and they did like a spectral decomposition. They looked at the matrix of the weight, and then they did a spectral decomposition, and that told us. So essentially what they were looking at, for instance, think of PCA, right? You have this point, and then there's direction of maximum variance. This direction now can be your canonical coordinate, right? Because now I don't need to consider all rotations of the points, because I have at least one coordinate that I know that none of that makes sense. So think about points that are ordered think of the point cloud of this cup, right? So it's clear that I could try to orient always this way. And then the only rotations that I need to consider are like this. I don't need to consider these rotations anymore because I have a canonical frame. Yeah. So the group that you're going to use is specific to each input, right? If I have a ball, then this would not work anymore.
So what do you mean is so like you have the data for each?
Yeah, so each element will have its own group. So for you see, because you right, so what you do is for each data point, for instance, you have a neural network here, you can compute this average embedding, right, for your neural network. So for that training example, we have an average embedding, and then you learn the parameters of this function here from that average. And then you do that for every single data point.
So at the end, you would have a frame for all the data points.
Yeah, so there is one frame for each point, but you are learning a function that embeds all of them. It's going to embed each one of them, each transformation. It's like, imagine like one way to be, so that's what based on the work that we have done. So imagine that you have this cup, right? One way to build an invariant representation would be I apply a neural network to this cup and this orientation, and this, and this, and this, and this, and this, all of them, and I average. Once I do that, right, no matter which orientation the cup is given to me, because I'm going to do all of them, my representation will be invariant. So it's kind of applied. So the idea that we had was we could apply the Reynolds operator instead of applying inside, right, the way that we were doing before. We are summing over the row 1 X, right? We apply on the other side of the neural network. And this neural network now is sensitive. It's not invariant. But because I'm averaging over all possible transformations, the final embedding is invariant. And then what I'm learning are parameters of this neural network that are sensitive. So when we talk about set representation, for instance, we are going to go over all permutations and apply an LSTM to each permutation. But in the end, LSTM will give us a embedding that is invariant. Of course, it's very expensive, and this is one of the tricks to deal with that. Actually, this has been quite successful in molecule generation. Like in molecule papers, they have been using this type of trick to improve the capacity of this network. because building equivariant neural networks, sometimes you end up, because of strict tractability, to lose a lot of expected power. And if you do that, you don't really. So essentially, you can prove that that these functions are G-invariant and G-equivariant, and essentially you can just replace the group averaging by some small subset. Okay, I think this is the part on G-invariant, G-equivariant network. We saw finite groups, we saw Lie groups, and then we saw this notion of averaging the embeddings. Are there any questions on this part? Yes.
I have a question. So in this, trying to sound silly, but when we determine the averaging based on the input, like which to average over,
Right.
How does the network know what the symmetry of the input is?
Yeah, that's a good question. Actually, the neural network takes no part in deciding which transformation.
Do we tell?
Yeah, we have to tell it how to do it. So imagine a point cloud, right? If you do PCA, you're going to find a directional maximum variance, right? And assuming that this is reasonably robust, if it's something like horizontal like this, then you can always give it canonically to the neural network, so you don't have to rotate from this maximum variance.
So if we have an object which is like the curve, for example,
Right.
we build the neural network that is symmetric, like rotationally it is symmetric.
Right, and that case, yes, if you have a direction, right, that is not clear, that can be canonical direction for your frame, then you have to apply all transformation. Because it may be that everything is symmetric, but there's some noise, and you're not sure how to deal with that, so you just apply the transformation.
So we have to tell the neural network if it's
I think that the one challenge is how to build a frame, and a frame that is robust to noise, which is very difficult. But it's kind of application specific. That's a really good question. Okay, so shall we go to sets? Okay, so let's talk about set representations. All right, so I'll start with transformers, I guess. Who here is familiar with transformers? Yes. Semi-familiar. Semi-familiar. Okay, good. So let me say this. I apologize that the notation is different, but we're gonna go through this and survive. So this is a permutation of this sequence, okay? I'm just permuting the indices like this, but it's just a permutation of the sequence, okay? So if I have a equivariant neural network, gamma, that if I apply to a sequence, right, the position, the if embedding is the same, but permuted, as we saw with equivariances, right? This neural network is an equivariant neural network for this permutation, okay? So the representation of the ith element does not depend on where it appears in the sequence, because the equivariance will force it to move, right, with the representation as we saw with graphs, please. Now, so what happens with transformers, if you think about it, is that they get the words, they input the ith word, and they add a positional feature. And then they go apply an equivariant neural network. And the transformer is that equivariant neural network. So that's how transformers work. So all these large language models are equivariant neural networks applied to an input that has a positional embedding. But if you go on GPT and you zero out this positional embedding, the whole network becomes equivariant all the way up. And I'm going to show a an example. So the thing is that, you see, this representation is going to be equivariant for this input. But for the original input, with which xi, it's not equivariant because you put the position as your feature. You see, that's the trick, that your position is a feature now. And therefore, for the original sequence is not equivariant, but for this new input, the whole network is equivariant. Okay, so let me show an example. For transformer, we'll do something like this. I have the words and I have my positional embedding for my words. I don't like avocado. Thank as my sentence. Okay, so the original data is like this, and I'm putting this positional embeddings. And now I'm going to use as input this x primes, which are these vectors. Actually, transformers will really, what they do is they have an encoding for the positions and they add to the embedding of the word. So that's what they do. But you can think of like this, I think it's easier to understand.
Sorry, question, but if that word, there's a certain position, then it's included.
If it, you see that, what is an equivalent representation, right? It means that the other words matter in your embedding, right? The equivalent means that where, if you give me a sequence, what the embedding does not care where in the sequence I am, but it cares about this the bag of words, the elements of the sequence, the set. So that's why this is a set representation, because it cares about the set. And the thing is that since the set has a position, it cares about the positions of the other words in that set. And I'm going to show the math soon, and that should be clear by then. Okay, so let me talk about just a little bit about transformers, and then we're going to set representations per se. I'm just trying to motivate a bit. So think about the self-attention graph that transformers have. It's a graph, has a vertex set and a vertex attributes, and the vertex attributes are these are gonna be these words with the positional embedding. Okay, so the edges of this graph here are actually the attention. So you get two words and you have an attention for these two words. And that's the attention between I and J. So the word I and word J, we have attention IJ, AIJ. And you can see that this attention is a function of the inputs, right? So this adjacency matrix here will then be the self-attention mechanism, and the values will be values between 0 and 1. Okay, so it's essentially mapping these elements of this sequence here onto themselves, right? So now if we add a positional encoding feature to the ith word, then you can see that that the feature of the vertices, like your attention, will also depend on your position. But if you remove it, it doesn't. So what happens then is that a transformer, essentially this attention is kind of a directed graph that you have, and each word embedding will depend on its neighbors on this graph. Okay? So this on the inputs where you are considering already the positional inside, this self-attention graph is going to be permutation equivalent to the representation of the sequence. So if you permute this, then the attention will permute with the nodes, but will not change, it will be the same, right? So this graph is permutation equivalent to permutations of this word position pairs. And you can prove this, it's quite easy to prove. So what the transformer is equivariant set representation with this positional encodings. Right, so as I said before, Let me show you the actual architecture, so I think it's easier this way. So essentially, your input is going to be this x prime, okay? Which is the word and the positions. And the query vector, tree vector, and values vector essentially build this this attention, the attention for each pair, which is just a function of the pair. And then you just sum them all multiplied by some the values vector. So it's essentially like it's a function applied to the value of each the input for each element, and then average over a function that is a function of that value and the neighbors, right, and the adjacency of the neighbors. So just like a graph, it's going to make it equivariant. Now, if you go and remove the positional embeddings, the entire computation will be given equivariant representation.
Is there intuition behind it? Finding that it's going to rate. Is there exponential distribution?
Yeah,
Why not something else? Why?
it could be any function. Like from a theoretical perspective, it could be any function. I don't know why attention specifically is that relevant. Probably is not that relevant. I think one of the things that is a challenge is you want the norm of this thing to be contained, because you don't want to see a new combination of things and have this function called something very different than something called. So that, for instance, once you're adding longer sequences, right, smaller sequences, you're not getting values that are too different. So the attention is kind of normalizing over the length, and that helps a bit with dealing with variable size. Because the transformer, if you look at it, in the computation in the GPU, actually, because of the efficiency for the GPU, you always have the same size block. You assume and you pad with zero. But the reality, if you look at this computation, it could be any variable size. You don't have to have a fixed block. It's just they have a fixed block just to be efficient in the GPU, but it's variable size. So once it's variable size, right, how you want the norm of these D embeddings to not vary too much depending on the size. Imagine if you're just summing things, then if you have a longer sequence, you get a much larger norm. If you have a short sequence, you get a much smaller norm. And this attention makes sure that you are averaging that out, like if the norm is average. It's one way to try to explain. Yes, definitely. I apologize that I didn't really mean to like go through the transformer, but I can do that. Because I have a transformer lecture and I did not do that. So essentially is this, you have this word embedding and you multiply by this weight here and you get this embedding Q. So this embedding Q is this times this, right? This embedding here, the K is going to be this times this for this one, and you do the same for the other element. And then now you do an inner product between this and this, this and this. And for the reverse edge, you do this with this. Right, so imagine like you can imagine like a directed graph with weights between edges, weights between 0 and 1. I'm creating I to j, and this is j to I. Okay, and the I to j goes in the I computation, and j to I goes in the j computation. And once I have this, right, this inner product is also normalized here. There is a reason for this, and I apologize, I was not thinking about talking about this, but there is a reason to do this. I think it because of the variable size thing, like I think it contains the norms a bit better. And then you do this sigmoid, right? This attention. not the softmax, right? The softmax over everybody, so over considering all the possible other words. And this creates your edge weight. So your outgoing edge weight sum to 1. Right? So that it kind of preserves energy if you want. So this defines this attention. And you can see that this attention, it doesn't really care where these words appear, right? The X prime and XJ appear, where they appear in the sequence is not relevant at all. It's gonna output always the same output, right? And then if you look at this computation here, right? I have, what I'm doing now is for all the words, I'm adding this V, which is the original input times this vector, this matrix, right? Gives me this vector. So essentially a kind of a weighted sum of this vector. And this will be the vectors of my neighbors, right? The other words, based on my attention to them. And that's my representation for myself, for my own word. And you can see again that this sum here is invariant permutation, right? It doesn't care about the permutations where the words are. So the entire transformer architecture does not care where the words appear at all. It's irrelevant, except that we are not operating on the original words. We're operating on the words with this positional embedding. So for the original words, it matters because the positional embedding is giving me different outputs for this function because of the position. So if you want a set representation, you can go to a transformer and say no positional encoding, and that's it. You get a set representation. So that I hope this is okay, like to motivate. But now let's talk about set representations, right? A set representation, you have a sequence, and you need to output the same, have the same output, regardless of permutations of the sequence, right? So you have a sequence of things. And one thing to pay attention is that the sequence could be, for instance, the point cloud, right? Each point has 3 dimensions. So it's actually, you get a matrix as input, and the permutation is just permuting the rows of your matrix. Okay, so we saw that before. And point cloud is an example, but here we're just dealing with the permutation of the points. We're not dealing with the SO3 or rigid transformations, right? We're just dealing with the fact that the order of the points doesn't matter. So one way to do this in a CNN, for instance, one way that you add invariances to a CNN is max pooling. Because if I have a sequence and I just select, I have a way to select the max value from the sequence. That is a set representation, right? The max is a set because it doesn't, the order doesn't matter. Average is a set representation. Median is a set representation. Okay, so one way, for instance, is do max, right? Because you know that this is invariant permutation. So max pooling is one of the simplest cases of neural networks that ensure permutation invariance. However, max pooling and mean pooling is a heuristic, and it's not that's not learnable, right? We don't learn it. So you have to be pretty certain that's a good set representation for you. What other heuristics are permutation invariant and can operate on any size inputs? That's an important feature set that have variable sizes usually. It doesn't have to be learnable, it can be a heuristic.
So it's a finite.
Yeah. Pro sum. Average, right? Yeah.
Maybe
Right?
I'm
The mode, yeah.
any moments.
Any moment, yeah. Computer science, something that for computer science we would say, sort.
Oh,
I can sort. And then I get this whole thing as an embedding, right? I can do whatever. I can pass an LSTM for a certain thing, right? I can do whatever I want. So some, right, mean pooling, median pooling, we can sort the whole sequence. And if once we sort the sequence, it becomes permutation invariant. Right, and what I mean by this arrow here on top of this neural network is really that it's permutation sensitive, like an LSTM or a transformer with positional encodings, right? But if I sort, I'm fine, right? Because sort is permutation invariant. Then what's the fuss about learning to do set representation? Because it's so simple. So consider the task we have a set here, right? Which is essentially a sequence, but I'm representing actually as a set here. And we have some training data. I have a set and an output, a label for the set. That's kind of what the task is, right? Now, so let me, before I go into explaining why these heuristics have issues, let me give you a kind of a statistical view of the problem. So you can think of these sets as a bunch of random variables, right? The elements of your set are random variables, and there is some from some space. And there is some probability associated with the sequence that you see right in here. So once you sample all of them, you have the first random variable, the second, the third, the fourth. Each one is an element of your set. You have n elements, and then you have a probability, right? That's how your data came about, the simple from the sequence. So what distinguishes in a probability distribution? What distinguishes the probability distribution of a sequence from the probability distribution of a set? Right? The probability distributions are always defined over a sequence, right? Your space is ordered. This is your first variable, second variable, third variable. So how do we define probability distribution over sets rather than sequence? It should be invariant to the distribution should be invariant to what? Sorry?
By enumerating the set.
Right. So all the permutations of the set, it should have the same probability. So it should have the same chance of getting any of the vectors that represent the set, because the order doesn't matter. Therefore, there is no information. There's maximum entropy for a given set of elements. There's maximum entropy. I cannot predict which order they're going to show because the order has no information. Okay, so that's essentially statistically what it means. So that the probability distribution is invariant to permutations. If it's not, then you have some information and you're able to better predict things, right? If it's not the case. So this in statistics is known as exchangeability, or more precisely, finite exchangeability. This notion that there is no information in the permutations. And there are a lot of applications, as you can imagine. One that I talked about in my talk was online shopping, right? You have a cart, the order of your products will not matter because you're buying all of them. So it should be a set. And set representations, as I said, have this permutation invariance. One thing, if you're familiar with De Finetti's theorem, like in statistics, it's an interesting thing because I don't know if anybody here or back may know was conscious when this thing happened, but when machine learning was very excited with hierarchical Bayesian models, very excited. So De Finetti was everywhere. Was kind of cited as the reason for like thinking about latent Richelieu allocation before, remember back in the day, right? So the idea of these models was that given some kind of condition, right, or cluster or some notion of a meta parameter, all your observations are independent. So for instance, in the case of NLP at the time, if you sample the topics, say sports, or evening news, then all the words in the text would be independent, given the topic. But the thing is that they prove this equality, that any exchangeable distribution can have a decomposition like this. But the thing is that you have to be careful that this theory is only true for infinite sequences. So if you have infinite number of elements in your set, then it's true that a mixture model can perfectly characterize your set. But that's absolutely 100% not true for finite sets. And that's why no matter how beautiful your Bayesian hierarchical model was, you could not perform that well because we were not accounting for this finite correlation. It's not just a mixture of independent things. So the thing, so I'll give you an example of why this idea. So whatever theory there is for infinite sets is very different for finite, and I'll give you one example. Is this: I cannot describe for instance, winning the lottery as a mixture, because only one person will win the lottery, and which person wins the lottery, it doesn't matter. Imagine everybody plays only once, right? So it's permutation invariant, right? You're winning the lottery, but only one will win. So you cannot describe as a mixture of independent samples, because if it's a mixture of independent samples, then more than one can win. That's not true. What is interesting is that because of the infinites here, statistical models cannot get this infinite correlation between the variables. Therefore, you can prove any model that can model this infinite correlation will have to be a mixture model like this, because the statistical models are incapable of that. But finite size that have correlations that you can model, right? You can say only one can. And that's the reason why these models, mixture models, are not that powerful, because they don't represent sets that well. Okay, so here is an example. Actually, Diaconis has a beautiful paper describing why that's the case, and you can it's there on the website. You can take a look and understand why this kind of independent mixtures are really poor models for sets. And when you have finite sets, it's really why deep learning is so important in set representations, because we really want to capture this really complex correlation. These mixture models are not good. Now, one thing that I want to say is, is it possible to learn a feed-forward network, right? An MLP that is able to have this property, right? Are there parameters in the MLP that would, for those parameters, my MLP would be invariant to permutation, right? Since we know that MLPs are universal approximators, it's true, right? It's true. But the thing is that since we are not forcing this, if we are not forcing this invariant, we will probably not get it. So just using MLPs for this, for sets, right, is not enough, because we cannot enforce permutation invariant. Okay, so let me then go through this idea. So let's then do what we were talking before, which is apply kind of the Reynolds operator, but over the embeddings, right? So if this F arrow is the neural network that's permutation sensitive, we get the embeddings for this neural network for all possible permutations of the input. And this, as we saw before, would be invariant to permutation, right? Now, let's try to make this tractable then, okay? So we are trying to learn this, the parameters of this neural network, which is this average, right, over all permutations. So this is our loss function. It's quite intractable, very difficult to do, but it's essentially a proper invariant representation.
So we have basically one label has for each set.
Right.
We have variable size.
They can have variable sizes. Then right, this function here you can think of like either a transformer with position encodings or an STM or RNN or a CNN. You can think of this as a variable size representation or variable size. That's a very good question.
And the only property we have to be the condition.
The function, the neural network, no, because since we are averaging over all permutations, we don't care. Right? Once we average over embedding over all permutations, it's not relevant if it's invariant or not. If it's invariant, it's easy, right? Because then this average here is just the same output as a function all the time, so you don't need to average. But if this function here has some sensitivity to some permutations, averaging guarantees that the sensitivity disappears.
And do you make any independent cluster?
No. No. No, yeah, I mean, the loss here is assuming IID samples from across here. Or even if you want, you can say it's permutation. It's not IID, but it's exchangeable. Like
Exchangeability is less strict than
it is, yeah, because as I was saying, for instance, the lot of winner is permutation invariant, right? It's exchangeable. So there'll be one, but it's not IID. Right? There's only one winner. So exchangeability is significantly less strict than independence. So this function here, right? I could put a permutation sensitive function, but I could also always sort the input, right? And therefore I get something that's invariant. Or I'm going to show another tractability assumption. That actually this tractability assumption is what describes all existing methods today for such representation, if you understand that way. Which is k-area dependencies. I'm going to explain that, and then I'll finally finish with stochastic optimization through random permutations, which is something that a lot of people use in practice. It works really well. Yes, this is correct, but not expressive.
An epsilon per your input.
Oh, this thing, yeah, this is a disaster. I'm going to talk about this disaster. Yes, you got it right. Because you see, the thing is that a good canonical ordering must be correlated with the task. If it's not, it's a terrible canonical ordering for you. So suppose that I sort my input, and there are two-dimensional input, and I sort in the first dimension, but the label depends on the second dimension, right? Now I am not really sorting. I'm just getting some arbitrary input because it has nothing to do. Now I'm looking at correlations between the ordering of the elements and the label. So it's as good as if I just didn't do anything and I looked at the sequence before. Does that make sense? Okay, yeah, that's exactly what I'm describing here. Some folks have proposed learning to sort, which is a very difficult task, but it could work, right? If you have a good way to learn to sort. Now I'm going to talk about tractability through k-area dependencies. And here's the idea. Think about this random type average, right? And I'm going to say that my function, whatever the sequence is, I'm just going to look at the first k element of a permutation. So for any permutation, instead of looking at the entire sequence, I'm just going to stop at k and forget the rest. My function is invariant to the rest. Just look at k. Okay, so that's what I'll do. Now, instead of having n factorial permutations, I have n minus k factorial over n factorial, right? N choose k, because I'm just looking at k, like I just need to permute the first k elements, right, to do this. Okay, so that's one way to make this tractable. Now, so one thing that you can prove then is that these representations are the higher order, meaning once you try to represent k instead of k minus 1, that is strictly more expressive than representing k minus 1. And it's always true for whatever k you choose. So there's always more power in representing larger, higher orders. Okay? So what is deep sets? I don't know if you are familiar with this method of deep sets. Is a set representation that is very much used. Well, deep sets is essentially k equals 1. That's what deep sets is. So you're essentially you're applying a function over each element of the sequence and average. You average them, and then that representation now is permutation invariant. You pass through an MLP. That's what deep sets does. And the set representation, right? So you're essentially just looking at the first element. Okay. So, but the idea is this. Now, what was proposed? So one challenge with deep sets is as follows: because you're only looking at each element at a time. And we know that as you go up in k, you are more expressive. There is really a tremendous lack of expressiveness from this embedding by itself. Okay? So, but this embedding, lack of expressiveness of the embedding, you can prove that is fixed by the MLP. The MLP then kind of undoes the sum and then find associations between the elements or higher order relationships. But it needs to undo the sum, and what you have, what you can see in practice in some applications, MLP is not up to the task. So deep set doesn't work that well in some applications because of that challenge that the MLP has. So another procedure is called the set transformer with k equals 2. What's the set transformer? Think of a transformer. Remove the positional embeddings. You got it. That's what the set transformer is, right? So it's equivariant representation. In the paper, they have some optimizations that you can do, right, to improve things a bit. But it's just a transformer. And there is also this other procedure called the set twister, which is kind of k equals 2, but is a lot faster than the set transformer because it tries to do pairwise. The function consider pairwise interaction. Okay. And the interesting thing about this, the higher k you go, it means that your neural network after that part can be simpler. Otherwise, it has to be quite complex to be able to get the interaction between the elements. And finally, you can talk about tractability through stochastic optimization by sampling permutations, and that's surprisingly effective. So again, you have this average, right? What you can think about is that instead of optimizing this loss, I am going to sample one permutation, compute this embedding, and then optimize my neural network just with that one permutation attempt. And that's it. And I keep doing that. Every time I do it, a gradient step, I'm sampling a permutation. Okay? Yes, it's a de-argumentation procedure for permutation. Yeah. So one thing about this, right? I think most people are familiar with Jensen's inequality, right? You know that the expectation of a function that is nonlinear is not the same as, may not be the same as the expectation of what's inside, right? Because of the nonlinearity, this is not the same. And you know that if alpha is a convex function, then you can bound, right, the expectation, this difference. So you can say, for instance, that minimizing, if you're trying to minimize this function alpha x, right, because this function is larger than this is a surrogate for optimizing this, right? Because it's always larger, right? That's the trick that we all use all the time in stochastic optimization. So essentially, you can think of this idea of sampling permutations as you're trying to do a stochastic optimization of the average over this entire neural network, right? So since you're doing this permutation sampling, this thing is a Monte Carlo estimate of this loss, right? Of the loss where there is an average over the entire procedure, right? But since it's non-linear, right, you cannot push the expectation inside as you would expect, right? If we could push the expectation of the permutation inside, then we would have the right procedure. But having it outside, since this loss generally is cross entropy or yeah, so you just do a stochastic. Since this is generally cross entropy, then this essentially is upper bound of your loss. So minimizing this will minimize the expected embedding from the averaging, right? So that's essentially the idea. Yeah. So this stochastic optimization actually is trying to optimize the correct objective. The only thing is that if you then try to use this neural network, it's better if you do some Monte Carlo sampling of the permutations and average them than if you use just one permutation in that. So that's essentially this part. And I think that's all I have to say for sets today. There are a lot of other kind of approaches to sets, but really, like for sets, I would say if you generally what really matters for when you're thinking about applying a set representation, what really matters is what K you are using. That's what dominates the expressiveness of your methodology. It's not the tricks and etc. Many papers, right? But really, the expressiveness has all to do with the K that you're using. And of course, the higher the K you have, the more elements you have to consider, more permutation you need to consider. So it becomes more competition here. Okay, so any questions on this part? On sets? No? Okay. Yeah, so I don't want to start graphs because graphs today would be a bit too much, yeah, a bit too much for everybody. Yeah, our next lecture or our next tutorial will be on graphs, and what I will do is I'll explain the difference between positional structural representation, how I can vector connected to graph neural networks, what graph neural networks can and can't do, and the many open questions that we have about graphs. Yeah, if you do have something interesting about graphs that you want to see, please let me know because we can just add. Okay, I think that's all for.
Thank you very much.